G'day, I'm Matthew Cutler-Welsh, the Education Manager at Clima for Australia and New Zealand. How much ventilation do roofs require, and where should that ventilation be to optimise the performance of our roofs? So our roofs in New Zealand and Australia have some issues. And mostly these issues are to do with the fact that roofs get really, really hot and they also get really, really cold. And the underside of roofs often get wet. Now in isolation, getting hot, getting cold is not too much of a problem. We can deal with that. Getting wet from time to time, it's not ideal, but we can deal with that. But when those things happen at the same time, it compounds these problems and we end up with some pretty serious effects. Firstly, moisture is not good where we've got any materials, particularly natural materials like timber. Often we're using things like paper as well as a membrane or an underlay. Even things like fiberglass, we know that moisture will impact the effectiveness of insulation, polyester as well, because we affect the amount of air that can be trapped, and we want dry air to be trapped to make the insulation effective. When the ability of materials like underlays to absorb water, which is what underlays are, particularly craft paper, is there for, when that it gets exceeded by the amount of moisture that accumulates, then that water's got to go somewhere. And it might go into the framing where it will do damage over time. If it sits around long enough, or even if there's enough humidity in the air where we've got metal fixings, that's going to lead to corrosion and other issues as well. In this particular case, we've got those combination of extremes. So we've got moisture, but we've also got very cold conditions. So we've actually got ice forming. That can also introduce physical stresses on the structure. As the ice forms, it expands and can push things apart, cause all sorts of problems. We can also get mold wherever we have moisture and we've got a food source, and we've got plenty of food sources within our building constructions with timber, cellulose. We get mold growth. A lot of people might not think it's too much of an issue up in the roof, but if air can get into the roof, and clearly it can because that's part of the problem here, that means that air can also get out, and with that can come mold spores. When those spores get into the living space below, that's when we end up with very unhealthy conditions inside the house. So they're just some of the issues that we have. A part of the reason that we have issues in our roofs is because roofs undergo some or subject to some very extreme conditions. Firstly, roofs get really, really hot. And we know certainly around most of Australia, we live in a warm climate. Even down the southeast corner of the country and down in Tasmania, it's classed as cool temperate, but we still experience pretty high levels of solar radiation. It also gets pretty cold, and this is something that we don't often consider enough, is the fact that where we live in Australia and also New Zealand, temperatures can get pretty cold and pretty chilly, and also very wet. In New Zealand, despite what some people think, we do get cold temperatures, and we also get a lot of solar radiation, and again we get a lot of rainfall and also high levels of relative humidity as well. So we've got long skinny islands surrounded by water. There's lots of water in the air, typically around 80% relative humidity and ambient conditions for most of the country. So roofs do it tough. They get really, really hot. They're facing that full brunt of the solar radiation, and we know of incidences from around the world where it's been documented that the roof surfaces can reach 90 degrees Celsius, and we're getting those sorts of findings in Australia as well with some of the research that we've done. In fact, some of our monitoring equipment goes up to 85 degrees Celsius, and that's pretty much the limit of some of the sensors that we've got. So there's a good chance that our roofs are experiencing temperatures in excess of 85 degrees Celsius. On the other end of the spectrum, our roofs also get really, really cold. And this is a example of my own house about a month or so ago here in Auckland, which isn't considered to be that cold of a climate. And this particular morning, it was 5 degrees in 7 a.m. in the morning, which is pretty cold. But this was the roof of my wife's car, and that's not dew, that's ice. So the question is, how does ice form when the air temperature is 5 degrees? Similarly, across the driveway, my neighbour's house had ice forming on a frost forming on the concrete tiles. And this is all due to night cooling, a night sky radiation, where there's a clear path there's no clouds and the air is still. There's a pretty clear pathway for long wave radiation to reach space, and space is super cold, close to absolute zero, so negative 275 degrees Celsius. Now there is an atmosphere between us and space, thankfully, but without clouds, there's still a pretty clear path, and that is why anything that faces directly towards space, like roofs, can experience temperatures at the surface of that roof that are well below the ambient air temperature. So the 5 degrees is what gets reported as the temperature, and that is the temperature of the air, but any surface can actually be colder than the air temperature. So that's a really important thing for us to remember, that during the night, that long wave radiation up into the sky can induce sub-zero temperatures at the surface of the roof, even if the forecast and the air temperature is above zero. Now, this is obviously going to cause problems if we get any air that has moisture in it getting into that roof space, and that will happen wherever we don't have an air tightness membrane on the inside. And that's best case scenario. Of course, in a lot of roofs, particularly in commercial buildings, we don't even pretend to have a ceiling. So even if we do have a suspended ceiling in commercial spaces, or even in most of our houses, there's so many holes and perforations that we don't really have an effective ceiling that is preventing moisture-laden air from reaching the cold surface of the roof. So a big part of the problem is that this is the way we've been doing things, and we know that condensation is going to occur, and we rely on a piece of material that's put there largely to absorb the inevitable condensation that's going to form on the underside of the, in this case, roofing iron, but it might also be tiles. And the idea here is that moisture might accumulate when it's cold, so for example at night time, and then when the sun comes out, heats up the metal roof, it's going to essentially bake the membrane dry again. That's all well and good, except that it happens day in and day out. And when that cycle is repeated, the underlay material is exposed to these pretty extraordinary conditions in a continual wetting and drying combined with extreme temperature fluctuations. And this is what we might do if we're trying to test a sample in a laboratory for accelerated aging. And that's not what we want in real life. What we can often find is that, particularly in composite materials where we get differential expansion and contraction, there might be tearing, and this is what we can see here with foil. Foil, by the way, is a really bad product to be using in buildings. Great for heating up things in the oven, but definitely shouldn't be used in buildings. There's no reason to use foil. That's a whole other topic. We won't delve too much into that. But the issues here relate to the expansion and contraction, and it's a very fragile material as well. So once it starts to tear, it will continue, and then it's effectively useless. We also, in example there from New Zealand, where we've got craft paper that has exceeded the ability to absorb the moisture that has accumulated on the underside of the roofing iron, and that's led to ponding. So we've got so much moisture there that we've actually got little puddles forming, and that's pushing down on the membrane. Any perforations, and you can see that there are some there, are going to obviously be a problem, because that water is going to find its way into the building below. And what often happens is that the occupants of that building call in someone to find the leak in the roof, and often there is no leak in the roof. The rain is essentially being generated from the warm, moist air inside the building, finding its way up to that cold surface and condensing, and that's where the water's coming from. We're also seeing patches of mold there, again, very far from ideal, because while that mold is in the roof, once it dries out and the mold spores become mobile, they will be able to find their way into the conditioned space. Not to mention the degradation that all that's going to have on not just the craft paper there, but also the other materials and products in that roof assembly. So this stems back to the way we've always done things. And here in New Zealand and in Australia, we've put membranes in place largely to deal with the symptom of condensation, with the intention that we can try and avoid the worst damage. But what we're seeing is that obviously that is not all that effective. So let's look at what the latest research is and common practices from around the world, because believe it or not, common practices overseas are very relevant to us here in New Zealand and Australia, because we have a similar climate. In fact, we're all on the same planet, so all the same physics applies, and we can find locations that either have a very similar climate, or even if they don't have a similar climate, the physics still works and the concepts still work. So we should be applying the latest thinking into our own buildings. So there's some great research from Philip Kolsch, who is from the Fraunhofer Institute in Germany. And Philip has been doing some great modeling and experiments using these test huts and looking at the temperature underneath the roof tiles in this case, but the same would apply if the roof tiles were switched out for metal, either long run or metal tiles. So by placing sensors all through that roof assembly, we can have a look at what the temperature is and also calibrate some of our hygrothermal simulations so that we can better assess what will happen under different conditions using ventilation at different rates and in different locations in that roof space. So one of the things to note here is that the data emphasizes just how extreme the conditions are in roofs. So this is a little plot of ambient temperature matched up with data from inside that roof in the same time period. Firstly, this looks like it was taken in summertime. Again, this is from Fraunhofer in Germany. And we can see their temperature range of the ambient conditions goes from about 15 degrees at night up to just over 30, maybe 32 degrees. So it looks like a summer period, and we're cycling between about 15 degrees and 32 degrees Celsius. So that's the air temperature, the ambient conditions. But what we can see in the roof is a much greater range of temperature that's being experienced. So it's getting down to nearly 12 degrees, so 2 or 3 degrees lower than ambient temperature at nighttime, but much, much higher, nearly 60 degrees Celsius in this instance, just under the roof during the middle of the day. And so this is just underlying what we talked about earlier, that the conditions experienced by roofs are much more extreme than even the diurnal cycles of temperature and humidity, and certainly the seasonal fluctuations in both temperature and humidity as well. So what Philip has suggested is that the air layer that we want to have in our roofs shouldn't be confused with the air layer underneath sarking or boards where the air is encouraged to move over the top of the insulation. This is not the ideal situation because that air movement doesn't contribute much to or anything to the cooling of the roof, and it also doesn't necessarily help dry the roof assembly out where we want it. But it's the way that we have been doing things, and it's the way that we've talked about roof ventilation. But the air movement in this location has some problems. We don't have separation between the cladding and the weather-resistant barrier. It induces some wind wash, which reduces the effectiveness of the insulation. Condensate that does form isn't necessarily going to be drained because the membrane is right up close to the roofing material. That can also lead to wicking of water where we have things touching the cold surface, and we don't really have much control of the system. So a much better way is to introduce the ventilation where we want it, which is between the weather-resistant barrier, the membrane, and the roof cladding above. So we've got this system of battens and counter battens, and we want to create a nice free space there for air to move up. And we're pretty familiar with this arrangement. We see it on walls as a drained and ventilated cavity. So it's something that we're very familiar with. We know how to do it. And this is what it might look like on a truss roof. It's exactly the same concept. In this case, there's a rigid sheathing underneath the weather-resistant barrier of the membrane, but which we would definitely encourage for lower slope roofs, but may not be necessary on higher pitch roofs. And as I said, it's very familiar to most of us. It's simply a wall construction tilted on an angle, and it becomes a roof. So this is what we're advocating for a cathedral roof, which has some significant advantages in general construction of going to a skillion or a cathedral roof. But bearing in mind that the more popular version in this part of the world is a truss roof, exactly the same thing applies, and we can also swap out the long run metal roof for either metal tiles or clay tiles. It doesn't really matter. The most important part is that ventilation space between the roof cladding and the weather resistant barrier below. A few people are taking this on board, and there's some really great examples of it being done out in the real world. So we're seeing more and more of this type of thing. This is a very nice example. And it's not necessarily anything new that we're pitching here as a crazy invention of ours. It's been done this way for quite some time around North America and Europe. And there's lots of details online about why it's a good thing and also how to actually implement it in the real world. So the benefits, just briefly, of this type of ventilation, which we're calling above sheathing ventilation. Firstly, the counter battens enable free drainage. So by lifting the horizontal battens up slightly, we're allowing a pathway for any moisture that does accumulate to run freely down to the eave. The air exchange cools the whole structure, so we're not exposing the rest of the house to those extreme heat conditions or to the extreme cold conditions either. And the movement of air contributes to significant drying of the whole assembly. So the main question is, does size matter? Now, if we take the issue of size to perhaps its natural limit, we see this type of design, which is like a parasol roof, where there's actually a secondary roof that's placed over the top of the conditioned space or the envelope of the building below. This allows for a huge amount of air movement and ventilation in between that top parasol roof and the space below. Great for very hot, dry places because we're basically adding a big sunshade or a shelter to the building envelope below. So lots of examples of where that's been done. But clearly we're not going to necessarily go to quite that extent where we have more standard construction. So the question is, how big of a gap do we actually need to take effect? Coming back to Philip Kolsch, his research looked at 3 different levels of ventilation, starting with low, which is essentially doing nothing special. There's no counterbatten here. We're just relying on the small gap that's formed by the regular battens that are there anyway to hold, in this case, the tiles. And we do see some benefits. So we're measuring the benefit in terms of the temperature difference between the ambient air and the conditions experienced by the roof. And the lower that temperature difference, the better. So we want the air underneath our tiles or the roof cladding to be as close as possible to the ambient temperature. And that's going to avoid getting that really, really hot condition in the summertime, and it's going to avoid getting the sub-zero conditions where we get night sky radiation. It improves if we add some counterbattens and we get what's called, or what Philip Kolsch has defined as, normal ventilation by allowing openable areas at the eave and at the ridge, and then we can further enhance that by going to strong ventilation. And the magic dimensions here are for normal ventilation to introduce an open area of 20 square centimeters per linear meter along the eave. And we don't need quite as big an area at the top. In fact, you want to have a bigger opening at the eave than at the ridge. So the open space at the ridge is 50 centimeters squared per linear meter of ridge line. To induce strong ventilation, we just double it. So we have 400 square centimeters per linear meter at the eave and 100 square centimeters of open area at the ridge. So in practical terms, this equates to a 25mm counterbatten for normal ventilation and a 45mm counterbatten for strong ventilation. So pretty easy to do, and we're getting more and more examples of this being done out in the field. What does cause some questions and does require a little bit of consideration is how to finish it off, particularly at the eave, with the connection of the roof to the spouting and how to finish the barge or the edge of the eave. But we do have some details for that, and we also have some details and can assist with the detail at the ridge cap as well. So head over to the ProClima website, and we do have a bunch of details there. There are more coming that are more specific to Australia, but we can help out with some guidance there as well, or point you in the right direction for detailing, particularly the eave and the ridge, but also the valleys and the ridges as well, that cause some consideration of how to incorporate battens and counterbattens of the appropriate size. So just to recap, the benefits of above sheathing ventilation are that drainage is enhanced because we're getting a free pathway for any liquid water that does accumulate to drain down towards the eave, to the eave. The air exchange helps for cooling, but it also reduces those excessive cold night temperatures as well. And the air movement greatly enhances the drying capacity of the building and the assembly. So that's pretty much it for above sheathing ventilation and the size required, the recommended sizes for that ventilation space. If you do want more details on this and any other technical information, head on over to either the ProClima New Zealand website or the ProClima Australia website. We've got lots of product information there, but we've also got construction detail library and our technical corner. And in the New Zealand website, you can also download a copy of the New Zealand study, which goes into a lot of the science behind this and some of the other topics that we cover. Grab a copy of that study. It's really beneficial to get a bit of a deep dive into the science, and it's also helpful to hand out to others, and also to give other people a bit of a guidance on some of these more technical issues. Well, that's it for me for this session. Thank you very much for listening in, and if you do have any questions, please don't hesitate to get in touch with myself or the rest of the team at ProClima.